In this video, we'll see how Huckel's rule for aromaticity arises out of the particle in a ring model. So we have our particle in a ring. We have our Hamiltonian is minus h bar squared over 2 times the mass of a particle times its radius from some point of origin here squared times second derivative with respect to this azimuthal angle here in polar coordinates phi. And we end up getting energy levels here that depend on a quantum number n. We get E of n equals h bar squared n squared over 2 times the mass times radius squared. And these integers can be 0, plus or minus 1, plus or minus 2, all the way up to plus or minus infinity. So we get 2 degenerate energy levels at each absolute value of n once we go beyond the ground state n equals 0. And our wave functions are psi n of phi is a normalization constant times a complex exponential. So if we look at what the form of these wave functions look like as we go around the ring here as a function of phi at the various energy levels here, at n equals 0, we've got 1 over square root of 2 pi e to the 0, which is 1. So the real part is all real, and the imaginary part is 0 all the way around, no fluctuation. At n equals plus or minus 1, the real part goes down and up once around the ring, and for plus and minus 1, they have different signs for what their imaginary part does, plus 1 being here, minus 1 being there. Then at n equals plus or minus 2, twice for the real part, and again twice for the imaginary part, but they have different signs. Same thing at n equals plus or minus 3. But what we notice here is we get this type of energy level diagram here as we go up. So if we have things like we have on the right here, where we have a system of p orbitals all the way around a cyclic ring there, we can approximate the pi system of these cyclic pi systems as being a particle in a ring model, and then see what consequences that leads us to. All right, so if we have things that have the structure of what we have up at the top here in orange, what we would have is, for example, with the cyclopropyl cation here, we would have 2 electrons. They would fill up those energy levels there, nicely fill up that n equals 0 shell there. If we have benzene, you've got 6 electrons going up, so you say 1, 2, 3, 4, 5, 6. You get nice full energy levels there. You get a nice stable configuration. Both of those, all energy levels are both completely filled. Same thing with cyclopentadienyl anion or cycloheptatrienyl cation. Both of those end up having 6 pi electrons and nicely fill up this n equals 0 and absolute value of n equals 1 energy shells there. But if we have situations like we have at the bottom, if we have the cyclopropyl anion, then what we have is this situation here, where we have a half-filled subshell at n equals plus or minus 1. Those are equal in energy, so we put 1 electron spin up in each of those orbitals. Same thing for cyclobutadiene, only half-filled. Same thing for the cyclopentadienyl cation, and at cyclooctatetraene, we would have 8 pi electrons, so we'd say 1, 2, 3, 4, 5, 6, 7, 8. And if you've been paying attention, you'll see that all of these molecules that I've grouped up here at the top would be referred to as aromatic in organic chemistry. And all of these that I have in the second row would be referred to as anti-aromatic. So we know that Huckel's rule from organic chemistry says that if you have a cyclic pi system which has a number of electrons which is 4n plus 2, then you get an aromatic system or a particularly stable arrangement of electrons. And if you have something that's 4n, then it's anti-aromatic, and that's particularly unstable, and in fact the molecule will try to distort itself out of planarity to avoid being planar and being anti-aromatic. So we can see very clearly here from the particle in a ring where this comes from. if we write out the number of energy levels up to a certain shell, like the number of energy levels up to n equals 0, we have one spatial orbital, and thus we can fit. So let's write, we have one orbital, and thus we can fit 2 electrons. If we go up to n equals 1, we have 1, 2, 3 orbitals, so you can fit 6 electrons. N equals 2, there's 5 orbitals, you could fit 10 electrons, etc. So you see, so the total that we can fit there for a given n is we have 2n plus 1 orbitals, so we can fit 4n plus 2 electrons. And you'll notice this 4n plus 2 means that we have a filled energy shell. It's particularly stable, and that gives us aromaticity. If you have 4n, then you have a half-filled subshell. So if I have 4n, gives me a half-filled subshell, and that's particularly unstable. So this very, very simple model system for a particle in a ring gives us these energy levels, which help to explain this observation about the behavior of these cyclic planar pi systems, and that you get the behavior of aromaticity is particularly stable because you've got filled energy levels, and anti-aromaticity being particularly unstable because you end up having these half-filled energy levels.